So in this meeting, I'm going to go over the schedule for the rest of this year. I'm also going to get into page 39 and 40 and how you're going to be able to get to that expectation. I'm going to go over what it is for energy, and I'm going to go into this conservation of energy. So I'm going to start off by getting into the schedule. As I get here, week 8 and week 9, the calendar and agenda. As we see with our calendar and agenda, it has week 8, week 9. Today, Tuesday, the 8th, we are zooming from 12 to 1. We're going to get into this types of energies. And so I'm going to focus on the different types of energies. And I'm also going to show you the expectation for 39 and 40. We're focusing on these different types of energies and then really this conservation of energy. We have a laboratory experiment. My in-person students, they'll be doing it when they come in person. My distance-only students, you're going to see a screencast I'm going to make. So that way you're going to be able to do the laboratory experiment on your own at home. So you're going to follow that screencast in order to do that laboratory experiment. Next week is our final week of our quarter. So on Tuesday, the 15th, this is the day of our energy test. On Tuesday, the 15th, we take our test. Wednesday, the 16th, that is the end. Everything that is due is due. So Wednesday, the 16th, everything by 3 p.m. If you have work to turn in from week 3, get me that work from week 3. Get it to me by next Wednesday at 3 p.m. You'll get full credit if you turn in by then. If you turn in after then, that's awesome. I'm glad you did it. But it's due by next Wednesday at 3 p.m. I can also look through my resources. As I see in my resources, I have I am on my resources. I have this work and energy, talking about what work and energy is, talking about what kinetic energy, gravitational potential, as well as this conservation of energy. What time does our final have to be turned in by? So it's not a final exam as I would necessarily call it. I would call it, if the test is just our energy test. So it's going to take into effect, or take into account rather, the information for this week and next week, just really about energy. So there's no final exam per se. I will open it up next Monday morning, and then it will be due by Wednesday at 3 p.m. So long answer to short is next Wednesday at 3 p.m. That's when everything is going to be due. So on our resources in week 8, week 9, we have these here available to us talking about what work and energy is. So you see, we have these different types of energies, and these different types of energies that follow along with that mental model, to where you saw an image of someone with a bow and arrow, we saw a rock, we saw a submarine, we saw a rocket ship, and really we're getting to these different types of energies, this elastic energy, kinetic, magnetic, thermal, gravitational, and electrical. These are all examples of these different types of energies. So you can use this here to see what these different types of energies are. We also have some different kinetic energy and gravitational potential energy. We have some equations for that. We have this equation here for our kinetic, which is that 1/2 mv squared. And if you see some calculations on how to calculate it, we also have our gravitational potential energy. This is mgh. So you can see the equations here. We're also going to have this conservation of energy presentation as well, so that you can look to see what's occurring here. What does it mean to have this energy be conserved? Where does this work part come in? So you can look through to see what this is saying. What it's really saying is the energy before equals the energy after. Just like the momentum was conserved, the momentum before equals the momentum after. Here the ball is up in the air, so it has all potential energy of 100 joules. That's a unit for energy. And we have kinetic energy of 0 joules. Then as the ball falls, it loses its gravitational potential and it converts it all into kinetic. So that it's all its potential transferred to a different form. And that's really what this conservation of energy is. So we have our schedule, we have what it is we can look at and use for this week 8 and week 9. I'm gonna go over to our class material packet. So back from our resources, if I look in this class material packet, this is where I'm gonna be able to find my page 39 and page 40. So we are gonna be doing that, and it didn't get printed in your take home packet, but I'll show you the expectation. But I'm just going from the class material packet, and I can look here to see what it is I'm gonna be working on, and I'll show you an example of what it is that we're gonna use and how you turn in your assignment so that way you have that understanding. So I'll show you later on in this Zoom session on what to do for this page 39 and page 40. What we're gonna get to now is what it is we're doing for these different types of energies. So we have what energy is. Energy is the ability to do work. So energy is this ability to do work. That's the definition. So energy is the ability to do work. That's what it is. And what we're gonna see is that we're gonna have work be done on objects, like gravity will do work on an object by pulling it down. There will be energy stored in an object that's lifted up to pull it down. So we have energy stored in the form of gravity. So we're gonna have this Eg be this gravitational potential energy. So we have gravitational potential energy. So we're going to use this term potential. We're using this term potential. So gravity, it could pull something down. So this term could is what's going to connect us back to this potential. Gravity could pull something down. Say, for example, I took this rag, and this rag is lifted up to a certain height. Gravity could pull this down if I let it go. If I let it go, gravity could pull it down, but I'm not going to let it go. So gravity could pull it down. So there's energy stored here in the potential in that it could fall down. Now, we don't know if it ever will fall down, but there's potential that it could. So gravity has energy there stored in this gravitational field. So it could be stored in this gravitational field. So energy is going to be stored in the gravitational field, so that way it has the potential to pull something down. And we're going to have an equation for this, Eg. is an MGH. So this gravitational potential energy, if you have the mass of it, the gravitational pull, and the height that it is up, then we will be able to calculate the energy for it. And this energy is going to give us a unit. These units for energy are joules. We're just going to go with the letter J. So energy has units. The units for energy is joules. And gravity has the ability to pull something down. We're going to have this gravitational potential as this MGH, where the energy is stored in the G field. I'm calling it the G field because it's the gravitational field. Now, once it does pull it down, giving it so many joules, then that potential could be converted into something known as kinetic. This E sub K, this is the kinetic energy. Kinetic energy is the energy of something moving. So it's the energy of something moving. If it's moving, it needed energy to get moving. And so now it has this energy of it moving, where we're going to have this EK having its own specific equation of 1/2 mv squared. So the energy of something moving is going to be this 1/2 mv squared. So since velocity can be positive or negative, if you square a negative, it's still a positive amount of energy. You get a positive value for mass, so 1/2 times the mass times velocity squared will give us our kinetic energy. We also have, with this kinetic energy, things can be moving. And let's say this ball fell, and it fell from a height, and it used its gravitational potential, and it goes into kinetic, and then it falls on a trampoline. Then it would be getting this EEL. This EEL is this elastic potential energy. So this elastic potential energy, so this is energy stored in a spring. So a spring could move something. That keyword on could is what gets us back to this potential. So a spring could move something, and it has the potential to move it. So a spring could move something. That's what this elastic. So we're talking about energy stored in a spring. A coil. And we're going to be using a new equation for this. This EEL is this 1/2 kx squared. K is a spring constant. And it has units of force divided by distance, newtons per meter. It's how much force do you pull on a spring and you stretch it out how far? That's what is constant about a spring. So if it takes more force to move it 1 meter, then you're going to have a higher spring constant. That means it's a rougher spring. If you get less force, less newtons, to go 1 meter, to stretch it out 1 meter, then it's a weaker spring. That's what the spring constant is telling us. How much force to make it stretch out 1 meter. So this spring constant is specific to that spring, saying about how much energy that it can store. If it takes more force to stretch it out 1 meter, then you're going to need more work to be done on it. More work to be done on it means more energy. So then that's going to bring us to our next topic, or our next type of energy. That we're going to call EINT. This is the internal energy of the system. So some people, like, really what it is, this gets down to particle motion, or heat from friction. So you could take your hands and rub your hands together. When you're rubbing your hands together, you're doing work, you're using energy. A lot of you would get tired, and then your hands, they get warm. Well, what you're doing is you're taking your energy of motion is you're having then your hands then convert that into heat. And you're doing it by keeping energy conserved. You're increasing the particle motion, the particles on your hands. So you're getting heat from friction. And so that's going to be really when we're having energy can go to this system, and it can go into this internal aspect of the system, to where it gets down to friction heat. That's just the simplest way to think about it. There's no specific equation for it. It's just about the system itself. As we get to this last one, though, work this is energy done on or by the system. So I could have a force applied for some distance. And that's gonna, well, it's gonna tire me out if I have to apply a force over an object for distance, because I had to do work. So this work is force times a distance. So we can see how much work to roll a ball up a hill. So if we are asked how much work does it take to roll a ball up a hill, and we can look at a couple different hills. I have 3 different hills here, all getting the same starting point. and they're all going up a height of h. If you get this ball, same ball, at all 3 points, and you getting this ball to go up this hill this way, or have this ball go up this hill this way, or this ball go up this hill this way, and they all get to the final ending point, you have to do work. You have to overcome that force due to gravity. So the force that's pulling this ball down is mg. So you have to overcome that force. Yeah, so you have to overcome that force, and the distance that you're going up is that height. So you did work onto this ball to lift the ball up. The work is just force times the distance, this mg. That's the force due to gravity down for the ball. You had to oppose that force due to gravity. You had to lift it up the height h. Same thing with this ball here. Still has the same mg going up the same height. So the work, which is force times the distance, the force of the ball is that mg down, and the distance you had to move was that height up. Same thing on this last one. The work is this force times the distance. The force is mg. The distance up is that height. So you get to a certain height. Now you have that gravitational potential energy of mgh that can then be converted back into kinetic energy, the 1/2 mv squared. But we're seeing that where this mgh comes from is this force, mg, times this distance, height. To where no matter the hill, it's the same height, so you had to do the same amount of work to get the ball up to that point. So how are we feeling out there right now? I've given us some stuff on energy and how it's the ability to do work. Do I have any questions from us out here? So what I'm going to move now is I'm going to move now to page 39 and 40, and I'm going to show us the expectations that we're going to be having from that. So for page 39 and page 40, we're going to be putting this on paper. And you can use notebook paper, you can use blank paper, you can use whatever you have around you. And what we're going to need to do is we're going to need to find what those pages are and where they're located. So if I go back to our Schoology page, and from within our Schoology page, I'm going to go down to our class materials. So by going down to our class material, and we're working on page 39. So I'm just going to go to page 39 in our class materials. And so this is what's going to look like when it's showing up. And so we are going to show that. So for page 39, we're going to be putting it on some paper, just as though we are doing it on paper. I want to point out that we do have our reference sheet. This reference sheet will give us our equations that we're going to use, this potential energy and this kinetic energy, There, you can also reference to in our reference sheets. So in number 39, we have a teacher example. So I'm going to work out the example, and I'm going to do the example on paper, and then I'm going to show you your expectations for 39, page number 1. So what I would like to have had if this had been printed off, where you're going to follow the system here. The system I'm indicating with a dotted dash line. And then we're going to label the energy graphs for 3 different points, point A, B, and C. So this is going to be point A, this is going to be point B, this is going to be point C. When I have this wind-up toy, it's going to have a lot of kinetic energy, and it's having energy stored in the spring. So I know it's going to have kinetic because it's moving. That's what this arrow here is showing. And this EEL, that's energy for a spring. So I'm going to make this qualitative. So I'm going to go up 1, 2, 3, 4. I'm going up 4 levels here. Qualitative in the fact that there's no numbers here. I didn't tell you that this wind-up toy is going 32.8 meters per second. All I'm giving you is that it's moving. So you're going to get the qualitative instead of the quantitative. Quantitative gives me quantities. Qualitative gives us the overall trend. So we have energy here in the form of this kinetic energy. We're also going to have some energy in the form of this elastic potential. So I'm just going to give it 1, 2, 3, 4 different levels on here. And then as it goes to point B, it's slowing down a little bit and it's unwinding a little bit. So it's going to slow down, so it has less kinetic. And the wind up has less as well. But what we need to have is we need to have energy be conserved. What that means is if I have 4 here and 4 here, it means I have 8 total. That means I need to have 8 as well here, to where at this point I have 2 and 2, that's 4. That means I have to have 4 go somewhere else. It didn't go uphill, so where the energy must have gone, it's gone into the internal parts of the system. So where the gears and everything have friction and it's interacting with the floor, that's why the floor here is part of the system. So it's rubbing on the floor, having friction, give energy there. To where we have 2, and we have 4 here, giving us that we have 8 total. And then lastly, at this last point, point C, it has all this internal energy where it goes up to this level of 8. So graph A, graph B, graph C matches up to points A, point B, and point C. And now we're going to do the same thing here for number 1, where number 1, we're going to have a point A, a point B, a point C, and a point D. Where point A, I'm indicating the system here with this dashed line around point B. And that dashed line, I'm including everything in the system. So it's a ball in this gravitational field. So for us on page 39, the way we're going to draw this out you're just going to label page 39, number 1, and we're going to have 5 different graphs. You're going to have an A, a B, a C, a D, and an E. And with these 5 different graphs, we're going to have now this A, B, C, D, and E match up to what we have here. Points A, point B, point C, point D, and point E. And what we're going to do is we're going to get the energies, either this EK, EG, or this EIN, and that's what we're going to be drawing in. So as this ball is starting, it's going up at this point A. So at this point A, it's going to have this EK going up to a certain level. And so what I'm going to label here is that it's going up to a level, and I'm going to have 8. 8 for my EK, just as how I had before. And then as it goes up to a higher level, it's going up to point B. Now my EK, and there's going to be some EG. My EK goes down. It's almost at the height, but it's still going up a little bit. It has more EG than EK. And I'm going to say that this has a level of 1 and this has a level of 7. So it's not always 8. So in this qualitative energy diagrams, there's no numbers given here. So with this, I'm just given an arbitrary. So when I'm saying 8, I'm only saying 8 because in these bar graphs that were printed, they went up to 8 levels. So I could, if I wanted, I could say that this has 100, and that this has a level of 10, and that this has a level of 90. And then that would also get to the same thing. Then at point C, this is when it's at its apex. When it's at its highest point, it has all gravitational potential. So the EK is 0, and this EG is all gravitational potential. So that's where all the gravity or all the energy is stored in this gravitational field. So that's once again where I'm going to give it this arbitrary amount, but keeping the total amount here constant, the same. So I'm going to have 8 before, I have 8 during, I have 8 at the apex, I'm going to have 8 as it's falling, and then I'm also going to have 8 at the end. So then I can go to my point D and E. As I look to point D and E, point D appears to be about halfway up. So point D appears at the halfway mark for the height. And then point E gets back down to the same height that we had at letter A. So here we had a height of 0. Point D is about a half height. Point C was at the apex. So if we're at half the height, then we should have, for our gravitational potential at point D, we should have half the gravity. So that's going to be at a level of 4. Where's the rest of the energy? Well, if we need to have 8 here, we're going to have the rest go into this EK. And then finally, the ball falls back down. And it's at this point E. And I'm going to say it has all EK yet again at this level of 8. So this is what I'm going to have here for number 1. As I continue, I'm going to show us number 2, and then I'm going to have you be able to get to your own for number 3. So page 39, number 1, I'm going to get to page 39. Or rather, now this is page 40. And we're going to look at number 2. So The ball is this system here. And I'm going to call this point A. This is going to be point B. This is point C, point D, and then point E. So then I'm going to need to have 1, 2, 3, 4, 5 different graphs. So I have my graph A, graph B, C, D, and E. So I'm going to label them A, B, C, D, and E. And then viewing this ball, we have this ball be a super ball, and it's dropped from a height, hits the floor, bounces back up, but it doesn't get to the same height. And it drops, and it doesn't get to the same height. So we know that energy is conserved, so whatever energy there is here, the energy is going to be the same here as it is here. So it has to go from one part of our system, and it's going to stay in the system unless it does work to an outer aspect of the system. So it starts off with all EG. So I'm going to give this a height of 8. And once again, I'm arbitrarily choosing this. I'm also choosing it because 8 is easy to cut in half. It's also easy to cut into quarters. So I'm choosing this purposely so it makes numbers later a little bit easier. So at point A, it has all gravitational potential, and then it's going to start moving, and then it hits. And as it hits at point B, we can say it has some kinetic because it was moving, but then some energy went into some other aspect. So it hits, and then it starts to bounce back up. So at this point B, we're going to have some EK because it was moving, but I'm going to say, let's say it has a height of 6. The rest of the energy is not going to go into gravity, but rather at this instant, it's at this internal aspect of the system. So we have some energy get lost due to the particle motion. So if you've ever bounced a bouncy ball, then you'll know what I'm talking about. In the ball, when it bounces, you hear it. You hear the bounce. If you hear it, that means there had to be energy there. So this EINT then would be up to a level of 2, to where 6 plus 2 is still 8. And then at point C, the ball goes up higher. So this is where at point C, the ball, which had kinetic and internal energy of the system, is now up. As it goes up, it gains gravitational potential. So it gains this EG. So we know it's up. But I'm only going to give it a height of 6. It got all that kinetic energy to go back into the gravitational potential. There's still going to be the internal energy of the system, the particle motion, still having that height of 2. Then the ball hits the ground again, except it's not moving as fast this time. And the system absorbs some of that energy into its particle motion. So now I'd say we're down to a height of 4. And once again, this is just arbitrary, giving them the internal energy of our system will also get a height of 4 as well. Leading us now down to our last one for letter E, where the ball is now up, but it's not as high as it was before. Because at point D, some of the energy went into the system, where the system is everything here, where it's the floor, gravitational field, and the ball itself. So at this point E, there's going to be some gravitational potential, where I'm going to give it a value of 4. And the rest of it, the rest of the energy is still in that internal energy of the system at this height of 4. So the energy of the system is still constant. So that's what we're showing here graphically. I know we haven't gotten any numbers yet, but we're able to show how this energy behaves. So we're able to show the energy as it moves from one form to another. So the ball didn't bounce as high each time, because the ball went into the surrounding parts of the system, to where the ball went into the internal energy of the system here. And then we can do the same thing as we have this clay, this piece of clay, it will not bounce. So this clay will fall, has gravitational potential at point A. And then at point B, it still has some potential because it's still at this height H. Then here it's half the height. And then here the height is 0, so it has no gravitational potential, but it's also not moving. So where did the energy go? So the energy has to go somewhere. And so you have to include the system being part of the floor here. So the energy at point A, point B, and point C, you're going to need to draw out graphs for point A, point B, and point C for this piece of clay dropping itself to the floor. I do have questions on the expectations here for page 39 and 40. So my hope was that 39, 40 was going to be an easy start for us. What I'm going to do now is I'm going to take us in to page 41. So let's go ahead and let's take out those packets that we have. Let's open up to page 41. So what we're dealing with here is mass that's moving, hitting a spring, and then not moving. So what we're gonna have here is this idea for this conservation of energy, where we're saying this energy before is going to equal to the energy after. This is just like how we did with momentum. We're going to deal with stuff initially and finally, where just like how we had with our qualitative energy diagrams, where we had 8 as the total for all times, now we're going to do the same thing, but now we're going to have the actual numbers. Now we're going to have some quantitative energy transfers where we're going to get the actual quantities. So what we're looking at here is with this moving cart that has this velocity, we want to know how much does this spring get compressed after it hits the spring. So the energy before is all in this kinetic energy. So the energy before is all kinetic, and this energy after goes into all the spring, which is this EL, that elastic potential. So initially, it's all kinetic. And then finally, it's this elastic potential. So now I'm going to refer to my notes for the equations that I need to use. So my notes, I had this gravitational potential energy. Well, did it go up or down? No, so I'm not going to use this one. We are using this kinetic energy, so this is the energy of stuff in motion. So I'm going to use this 1/2 mv squared as the kinetic energy, and my elastic potential energy, well, this is talking about a spring, so I'm going to use this 1/2 kx squared. So my kinetic, which is my EK, is my 1/2 mv squared. It's going to equal to my kinetic energy, which is my 1/2 mv squared, going to equal to my elastic at 1/2 kx squared. And it's asking how much is the spring compressed. So this x, this is how much the spring is stretched, compressed, so that's what we're going to try to solve for. So I'm going to get rid of these 1/2 by multiplying 2 on both sides. And I'm going to move the k to the other side. So I'm going to have mv squared on k equaling to this x squared, giving me an x is mv squared on k square root, where it tells us what the mass is. The mass is that 8 kilograms. It tells us the velocity, 5 meters per second. And I'm divided by the k, which is that 50 newtons per meter, and square root. 8 times 5 is 40. 40 divided by 50. So I'm going to get 8 times 5, which is 40, divided by 50, and then square root. So that way I get my 0.894. So my x is 0.89 meters. So I was able to solve this because I know that this was moving and it hit the spring. So the spring energy is the EEL, the moving energy is that EK. And if I set them equal to one another, when I know M, I know V, I know K, and I know V, then I know the energy before is going to equal to this energy after. Using the energy before, EK, and the energy after, EEL, I'm able to solve for the value that I need to know. So here, this is talking about how much the spring is stretched or compressed. That's this X. So I'm able to solve for that in terms of the variables. Sometimes I know you guys just like to plug in the numbers. If that helps you, do that. It's oftentimes more beneficial to use the variables, so solve the letters first. So I get the letters by itself, and then I put in the numbers. So number 1 here is a little tricky. So we want to get the velocity of the cart, assuming that 10% of the energy is dissipated by friction. So we know that it starts off up at a really high peak. From this high peak, then it moves down and is moving. It loses some energy to friction. So it starts off all gravitational potential. Then it's moving, so the final is going to have some energy of it moving, and we're also going to have some energy of it by friction. So that's where I'm going to put in this amount over here. So I put in this amount on the right because some energy is lost to friction. Now it's 10%. So graphically, the way it should look, if this is 1, 2, 3, 4, it should actually graphically only be about to that height. So graphically, this is not correct graphically, but I'm showing it so it's visually able to be seen. So you can tell that if we have 8 before, or if we have 10 before, then this would be 9, and this would be 1. So if this was 10, 9 plus 1 is still 10. Where this 1 is 10% of the original. So what we're being asked to find here with number 1 is the final velocity of this cart. Where we know initially it starts from rest, and it has mass of 20 kilograms, and it starts from a height of 5 meters, and it loses 10% of the energy. And it doesn't get lost necessarily, that like we can never find it again, but it goes into a different form, this E internal, this internal energy of the system. So we're going to do the same thing that we're going to have here for this conservation. Conservation is before equals after. When we had conservation of momentum, it was PI equal to PF. Now we're having conservation of energy where it's EI equal to EF. This energy is conserved in that it doesn't go anywhere. So the energy before will equal to this energy after. So the energy before, as we were saying, is all gravity. So the energy before is all gravity. So it's all this EG. And the energy after, as we were saying, is this EK plus the EINT. So it's EK plus the EINT. So gravity first, then after it fell down the hill, it was moving and some of the energy was lost to friction. Not just some of the energy, 10% of the energy. So if this energy here in the beginning was 100, 10% of it was lost due to friction. So we're going to say then that this EG, which is now equal to EK plus the EINT, it's going to be plus 10%, so that's going to be 0.1 multiplied by the energy it had before it fell. So this EI, 10% of that energy was lost due to friction. That's what we're going to be able to say here. So that EI is this EG. So EG is going to equal to EK plus 0.1, 10% of that EG. Because the energy before was gravitational potential, and that's all the energy of the system. Everything that was there is there. And 10% of it is lost to friction. So then what we're left with here is now EG equals EK plus 0.1 of EG. I'm going to move this to the other side by subtracting by 0.1 EG, giving me over here a 0.9 gravitational potential is equal to EK. So now I know this 0.9 of my mgh is equal to 1/2 mv squared. So we don't need mass, it cancels out. We know what G is, we know what H is, we just gotta solve for this V. So I'm gonna multiply by 2 on both sides, giving me that V is gonna equal to 2 times 0.9 times G times H. That got rid of the 2. And now square root. So I have the square root of 2 GH times 0.9. And that's just going to be the square root of 2 times 0.9 multiplied by that 9.81 newtons per kilogram, or meters per second squared, times a 5 meter height. So 2 times 0.9 times 9.81 times 5, square root. So we get a 9.396, so 9.40. So this V is a 9.40 meters per second. So I went like step by step by step by step. So for your problem, you have the energy before, all gravity, energy after, which is this kinetic, plus the internal energy. Energy before equals energy after. I know this internal energy of the system had 10% of the energy lost, total energy lost. The total energy was this EG. So they had then 0.1 of that EG, allowing me to set now EG equal to this EK, solving for the velocity.